I am postdoc at, as some other pointed out, I am postdoc at Institute of Frontier and Fundamental Science in STC, which is in Chengdu, China. It's the western part of China. Very vibrant, colorful, tea drinking, laid back city, cultural city like Kolkata. So it's a very beautiful city. Today I will talk on the identifying the resources for 2-to-1 random access code and how this identification will give us some advantage in sequential communication protocols, and that equivalently meaning recycling a same qubit resource arbitrarily many times for 2-to-1 random access. This work I have done with the collaboration with Shom and Devorshi. Shom is now postdoc at Portugal, and Devorshi is assistant professor at Shivnadar Institute, Delhi. So this is our paper. Actually, we have written recently the unbounded communication power of a qubit, but I must say this is not in terms of Kolevo power, because in one qubit only associated with 1 qubit of communication. This is how we interpret this unbounded communication, that is in terms of the sequential advantage that many receiver can decode encoded information with quantum advantage. Now the fundamental.
So we are getting recorded, so it's okay with you, right?
Yes, yes.
I think you mentioned it. No, I think
privacy statement. I have to tick
once.
Yeah. So basically, the fundamental difference between the classical information theory and quantum information theory is the bits used in this two theory. In classical, it is C bit, which is 0 or 1, like red ball or blue ball, and no superposition of the C bits are allowed. And for quantum information theory, this is qubit, and qubit means 2 vector in Hilbert space, and their superposition of 0 and 1 allowed. Although Kolevo showed that 1 qubit can only carry at most 1 qubit of information, but there are several communication tasks where it has been shown using qubit is more advantageous than a classical bit. For example, this task called, if we consider this type of communication game called 2-to-1 random access code, 2 means Alice has 2-bit string, which I denoted as x, x1, x2, which can be like 0, 0, 0, 1, 1, 0, and 1, 1. So Alice has 2-bit message, and Alice is only allowed to send either 1 qubit or 1 qubit to Bob. And Bob has an input y, which is 1-bit input like 1 and 2. And depending on the input of y, Bob has to guess the bit string Alice sends to Bob. That means whenever the game will be on, if Bob gets b equal to x subscript y, that means Alice can either send x1 information about x1 or Alice can either send information about x1 or information about x2, because she is restricted to send only 1 qubit information or 1 qubit. So in this, if this is called 2-to-1 random access code. Why this is 1? Because 2 qubit, because Alice has 2-bit message and Alice can send only 1 qubit or 1 qubit.
So when Bob wins,
the winning condition is if Bob's outcome is equal to xy, the Alice's encoded bit. That means if Bob can predict what message Alice sends. And as you can see, since this is a 2-bit message, that's why Bob cannot win all the time with probability 1. So sometimes Bob will guess correctly, sometimes Bob will not. So even.
So I'm just thinking this, I don't know about the random access code, but I was just thinking this is a very similar to the ICTs.
IC principle. Actually, IC principle is based on this type of communication.
If you can gain more than, then it violates IC.
Right. If you can get more than what quantum of, I mean, there is a IC bound, which actually coincides with the quantum bound. However, recently Manikda and also Golokda's group shown that in this type of measure game, in more general scenario of random access code, they have shown that there can exist beyond quantum correlation, which can violate IC. Manindra first pointed out. So IC may be the boundary of quantum, and then all of this group have shown that there exists beyond quantum correlation which satisfies IC. But anyway, quantum correlation has to satisfy IC. But that does not preclude, there does not exist any theory which is bigger than quantum, but satisfy IC. That exists. This kind of bigger quantum theory exists which satisfy IC.
But I have this small question. So if you have three, so if X was instead of X, oh wait. Oh, it's just a bit, okay. Sorry, I thought you had two X's that were both 2 bits, but I guess you have only one X, which is 2 bits.
Exactly. X1 is has 1 bit information, X2 has 1 bit information. And also this type of IC, and whether the quantum boundary is same or not, those for 2 to 1 RSC, it becomes almost same. Same. People have not found any exception. They had to go beyond 2 to 1 RSC.
So this so to get around correct. So if you're going from N to L, then it would be that X is an N-bit string, and you're sending at most L bits of secrets.
L bits of information.
Yeah.
This is the simplest scenario. That if Alice wants to send 1 CBit, then the scenario is trivial. I mean, 1 to 1 RSC is trivial because success probability will be always 1. Since it is 2-bit information, Alice is trying to send with 1 CBit. That's why it is the success probability cannot be 1. So what is the success probability? Success probability is the 1/8 of each event. Why 1/8? You can see there are 8 possible events. Because X1 and X2, there are 4 types. I mean, Alice can prepare 4 different types of preparation depending on which bit Alice received, and Bob has 2 inputs. So there can be 8 possible events. So whatever the 8 event probability, outcome probability will be in Bob's side, we have to divide it into 8 to get the average success probability. And it is when the success will be B equal to XY that I have given. Now, when Alice sends 1 CBit information, that we can say that in classical bound is 3/4. And why it is 3/4, that will be intuitive when I will introduce the previously unexplored resource in 2 to 1 RSC, then it will become why this 3/4 bound is there. Also, Specans also derived the same bound from a non-contextual ontological model. That means if Alice uses a non-contextual ontological model to send some information to Bob, then also Bob's average success probability will be bounded by 3/4. But today I will not go into those concepts. Let's take it as a 1 CBit bound. Now, when Alice sends qubit communication, then what happens? Then actually Alice's preparation is density matrix, which is the first postulate of Copenhagen interpretation, standard interpretation. And after sending the qubit to Bob will perform measurement, which is characterized as POV. POVM is a set of positive operators which sum up to identity. That means splitting of identity is a quantum measurement process. In that way also we can see. And then the probability will come from the trace root, which is again the postulate of the standard interpretation. So in quantum theory, the whole game is Alice will send 1 qubit, Bob will perform POVM, and then collect the statistics in terms of trace root. And people have found that the optimal success probability, this is around 85%. That means which is greater than 3/4. Why I wrote sometimes? Because there may exist some set of density matrix, some set of POVM, such that the success probability is less than 3/4. Those resources, we will call it as a classical resource. Why? Because it will not give me any advantage over 1 CBit communication. So for those resources, we will not try to experiment with quantum resources. We will just experiment those in classical CBit information, using classical CBit. Now, one thing we need to understand here that when Alice is sending Bob for the optimal success probability, Bob needs to perform a special type of POVM, which is called projective measurement. projective measurement means each effect operator square is equal to effect operator. Physically, one can understand in this way that whenever Bob performs a POVM, it splits the Hilbert space into two subspaces. Now, if these two subspaces are orthogonal to each other, then there is no overlap between these two subspaces, and one can distinguish the two outcomes precisely. This is called projective measurement. A general POVM can be a general, like if there is an overlap between these two subspaces or if those two subspaces are not orthogonal.
So if Alice is sending the Bob the qubit, it is independent of using an entanglement, right?
Right, there is no entanglement. Alice will receive one input, Alice will prepare a qubit according to that input, and then Alice will send that qubit to.
And if they do have shared measurement, shared entanglement, does it help?
I will come to that. Yes, entanglement will actually help because entanglement is another resource. If you can add more resource, it will help eventually. But I will.
This is very interesting in context of entanglement. Suppose if I want to send a qubit, just teleportation in entanglement. That limit, there is also such a quantum advantage limit, 2 by 3.
Right.
2 by 3. And some entangled states are not useful. Some entangled states are useful.
Right. Here also, some preparations are useful and some preparations are not. Maybe one can ask those preparations who are not useful, whether if you put an entangled state between as extra resource, can it be useful? Yes, it can be. We will have shown it. So entangled assisted RSC scenario is little bit complex than different. So my point is to remember that whenever Bob will perform measurements, since quantum measurements are inherently invasive, it's not like classical measurement where we reveal the value of a property of a system. Quantum measurement actually changed the state. That is the postulate, at least according to the Copenhagen interpretation, that since the decoding measurements being invasive, that will destroy all the encoded information. So if Bob wants to give this qubit to another receiver, let's say Charlie, that Charlie will not get any advantage to decode the information, whatever Alice encoded earlier. That information will be, the success probability will be always less than equal to 3 by. Now let's consider this type of scenario when we go beyond the standard 2-to-1 RSC, that Alice sends her qubit to Bob 1, and then after performing some measurement, Bob 1 will transfer the qubit to another receiver, Bob 2. And as I have mentioned, if Bob 1 performs projective measurement, then Bob 2 will not get any quantum advantage. However, if Bob 1 performs a noisy version of projective measurement, that means it is a convex mixture of projector and the white noise. Then the subspace, after the measurement, when the Hilbert space will be decomposed into two subspace, those two subspace will not be orthogonal. There will be some overlap. And in that way, maybe Bob 1 will not get the optimal advantage, but Bob will get some advantage, at least greater than 3 by 4, and some information will remain in the queue. Then Bob 2 can perform another measurement and try to decode that information with quantum advantage. Now, people have shown that if Bob 1 performs both the measurements, if Bob 1's both the measurements are unsharp. Unsharp means that is the noisy projective measurement. I will come to that, how unsharp measurement is defined. Then this paper has shown, even with an experiment, that only two receivers can get the quantum advantage simultaneously. Also, these two receivers must be independent. What I mean by independent, that means Bob 2 does not have the information about the input and output. Because if Bob 2 has information about one Y and B, then the game will be trivial. Bob will not perform any measurement, he will just photocopy the result. Also, one may ask that if Bob 2, let's say, does not have information about Y, but has information about B, then what will happen? Then you see it will not be a 2-to-1 RSC between Bob 1 and Bob 2, it will be 2-2 RSC because this B carries 1 bit of information. So if Bob 2 knows any one of the information, it will not be the 2-to-1 RSC. So in that way, Bob 1 and Bob 2 has to be independent. One can think of it like Alice as a bank and she wants to communicate some message regarding the password, and different Bobs are different customers. So with a single qubit, can all the customer get the relevant information or not? And usually the customers are independent.
Then shouldn't the bank send the information and not the first customer to the second customer?
I mean, one can think of it in a different way. Let's say one has to come to the bank to press a button and get some information and go home. Then the next customer will come and press the button and get the information and go home. In that way also one can think of it. But really, whether it is that much useful, that I don't know. I'm just giving a broader motivation of realizing the importance of sequential. So our central question was that is this the ultimate communication power of qubit? Communication power not in the hollow sense, as I have said, because a qubit only carries one qubit information. In the sense that whether there exist many number of receivers who can get the quantum advantage. So in other words, you can pose this question in this way, that how long does the information encoded in a single qubit remain accessible even after multiple decoding? So why I put this question in other words, because in a noisy situation, if I know this result, then let's say there are only 2 receivers, but there is a noisy environment. Then how long this encoded qubit can retain the information so that the Bob can get that information. So this type of, in those scenarios, this interpretation will be more important. So what we have shown that arbitrarily large sequence of receiver can obtain quantum advantage, and even after repeated measurement, the information encoded in a qubit need not be entirely exhausted. So one can also interpret like it may achieve like a genolike feature. Like let's say when Alice sends the qubit to Bob, there is a time-dependent Hamiltonian which is trying to change the rule. So if Bob1 performs repeated measurement, then Bob can mitigate the effect of time-dependent noise. So in that way also, if this framework will be useful. So of course, if Alice sends 1 qubit, then Bob1 sends 1 qubit, Bob2 sends 1 qubit, then all Bob can achieve success probability less than equal to 3/4. And to get the quantum advantage, every Bob and every Alice and each Bob need to access the quantum system. And in between, if any Bob gets the optimal measurement, that means that Bob performs projective measurement and all the encoded information will be destroyed. So now one can ask that why not just use entanglement? Because recently it has been shown that in CSSH scenario, the non-locality can be shared among different observers like Alice Bob1, Alice Bob2 with arbitrary number of Bobs. Then why we need this 2-to-1 RAC like scenario? Then why we use prepared with that scenario? So one problem is with Bell CSSH, it is very experimentally demanding. There are several loopholes to perform the experiment: detector loophole, locality loophole, free will. Also, Bell experiments are very resource consuming, and prepare measure scenarios are more simple to implement. There is no specialized correlation we need to satisfy, less explored, and also it manifests new type of quantum correlations like contextuality or Leggettgard like correlation in time domain. Also, there is a very interesting thing will happen in CSSH case when if there is an entangled state, if Alice will perform A0, it will create 2 orthogonal state in Bob's side. If Alice perform A1, then another set of orthogonal state. But in prepare measure scenario, Alice's 4 preparation can be arbitrary. So that means we can charge to a larger set of RAC resource. So in that way also one can think prepare measure scenario may give more advantage. However, recently Baroni et al. Has shown that CSSH scenario can be mapped into 2-to-1 RAC scenario. So in that way, whether this result can easily follow in this setup, and it will make the problem trivial. However, the problem they have not explained that what is the resource here, because for CSSH explanation you need measurement incompatibility and entanglement. Here, to get the quantum advantage, Bob's measurement need to be incompatible. That resource is there. But what other resource is there which will replace this entanglement, that is not there in the literature. So we have first identified this resource, what is the necessary resource for 2-to-1 RAC, then we connect it with measurement incompatibility, and then we show that this kind of thing will also happen in this prepared measures.
One question. Okay, before this, like when we are trying to see the advantages of 2-to-1 RAC, which like you were saying in the Bell scenario, we need to ensure like space-like separation, like some space correlations which are hard. But even in this 2-to-1 RAC, you need to ensure that exactly one message is being, one bit or like one qubit of information is being sent, which is also a correlation which is hard to ensure. Like,
in principle, you can ask that, but really, if I prepare a qubit and if I send the qubit, then it is not that much easy, right? Because it is not space-like, it is not time-like separation.
like I was just asking this because what if, what if I just prepare 2 qubits and send 2? Like ensuring that only 1 qubit is sent seems to be a bit hard, right?
I don't get it. Let's say we are operating
Sending something through a fiber optic, right? Like it's hard to say, for example, only one photon is going, things like this. Like how do you make sure that
this is hardware problem, right? In principle, I am saying.
No,
So
then by principle, you can also assume spatial separation. He's saying just as spatial separation is hard, you also have a problem here. That's all he's saying. I don't think he's saying anything.
this kind of problem may arise there, but still in space-like, to ensure space-like separation, you need more resource because you have to ensure that the experiment is happening in less than the time photon travel time, and that control is a little bit
That is at least one way of ensuring that the assumption of no communication is enforced. In your case, it's not even clear how you would enforce
Okay.
Right? Like, so you're not making a fair comparison. But that's okay, doesn't matter. Carry on.
So yeah, so we have identified that the new resource which we call preparation distinguishability from in sender side. In receiver side, measurement incompatibility is the resource, and in preparer side, preparation distinguishability is the resource. And then we have connected these two concepts, preparation distinguishability and measurement incompatibility, and proved that how RAC success probability can only be dependent on these two resources. So to define preparation distinguishability in a operational theoretic sense, operational theory in any operational theory, the primitives are preparation, transformation, and measurement. I have not written transformation because here I will not talk about it. So a preparation procedure is a preparation specifies a procedure for generating physical systems according to some ensemble description. And the measurement is a test applied to those systems producing outcome with some probability. Example, standard quantum mechanics is an operational theory where the preparation is density matrix and the measurements are characterized as POV. And another example is classical statistical mechanics where phase space of a simple harmonic oscillator can be thought of as a preparation, and function of a phase space is the measurement. Function of a phase space means which maps the phase space to the real number space to reveal some data about the system. And also classical statistical mechanics is also probabilistic. So we define the preparation distinguishability in this way that if we have two preparation, P0 and P1, and those two are different preparation, and one may ask that how you say those two are different preparation operationally. So we define, I will come to this point. So we have defined that preparation distinguishability between P0 and P1 is the maximum total variational distance between their outcome distribution optimized over all possible measures. That means this we have denoted it with delta, and delta is equal to probability of M for P0 preparation minus probability of same outcome for P1 preparation. We have taken this bond because sometimes may happen the probability of N with P1 preparation can be bigger than the preparation P0. And why we put this half? Because we like to have this delta to be between 0 and 1. So it is just a scaling factor. And then we optimized over all possible measurement to get the maximum total variation list. This is our definition of preparation distinguishability. And when preparation distinguishability is 0, that implies no measurement can distinguish P0 and P1. That means they are operationally equivalent. In quantum mechanics, I can give you an example. Like, let's say if I prepare the maximally mixed state I/2, I can prepare it from taking equal mixture of two eigenstate of sigma j. Or I can prepare by taking two eigenstate of sigma x. Those two I/2 in quantum mechanics are operationally equivalent. If we can distinguish them inside quantum mechanics, it will violate no signaling principle. But that is the discussion. The argument is way beyond my today's talk. And
When it will violate, you can distinguish only if you have an access to the just an trivia. If you can access to it, Deutsch citizen close time like. So, so this is a very interesting. So you raised a very interesting point. So this sort of proper and improper mixture. If you can distinguish between a proper and improper mixture, only if you have an access to the closed line mega, and that access tells you there is a valence signaling. So you can that access tells you there is a signal. Okay.
I was thinking of that argument that if you have a maximally entangled state between Alice and Bob, if Alice measure sigma j, Bob's state is I/2. If Alice measures sigma x, Bob's state is I/2. But their preparations are different, right?
Now, normal quantum
exactly. You cannot do yes. Now, if Bob can discriminate between these two preparations, so Alice is essentially sending 2 bits of information. So it will
signal. And in normal quantum mechanics, you cannot do it.
Exactly.
But if you think that if you have a kind of a black box, which is a kind of a global unitary operator, and one of your qubit is causality respecting another qubit is a CTC going around in time. So, and there will be two kinematic condition to solution. With those two nonlinear equations, you can distinguish the mixture.
Okay, great point. And if delta equal to 1, then there exists a measurement that perfectly distinguishes them. For example, the two orthogonal states in quantum mechanics. With one optimal measurement, I can perfectly distinguish. So now, what we have first proved that this preparation distinguishability has some operational meaning that I just told in terms of the preparation discrimination task. That if someone gives me P0 or P1 and I had to tell which preparation they give, then I had to perform some measurement and I had to come up with some strategy. That let's say whenever I will observe m equal to 0, I will guess the preparation was P0. If I get m equal to 1, I will guess the preparation was P1. So my average success probability then will be sum over probability of obtaining n. I mean, has to be scaling with half because there are two events. And then I need to optimize over all possible measurement. And that optimal measurement is called L-stop measurement in quantum mechanics. This is just a name. And then after just few algebra, we have shown that this preparation discrimination task optimal success probability is linked with the preparation distinguishability.
So the difference is just that you have essentially a convex mixture of prepare and measure.
Right. Now let's come back to the 2-to-1 RAC. In 2-to-1 RAC, let's say Bob receives the input y equal to 1. Then Bob's task is to guess x1. Okay. Now x1 can be 0 or 1. If x1 is 0, then Alice's string is 0, 0 or 0, 1. If x1 is 1, then accordingly Alice's string is 1, 0 or 1, 1. You can see I have written in this notice x1, x2. So the first bit, the second bit, we need to take both, and the first bit is fixed on the task which input Bob has received. And then, so whenever Bob receives x1 equal to 0, then Alice preparing this marginal P01, preparing either P00 or P01 with equal probability. Now, how to define this P01? This I will say this sub-ensemble that will depend on the theory. For example, for quantum mechanics, I can take it as a convex mixture of two density matrix. That I will come. And that's why I have written it in English, not in mathematics. And when the preparation is x1 equal to 1, Alice will prepare either P10 or P11. Now one can ask that this input Bob receives later after receiving the system, then how Alice will know that? I am saying that one to identify the resource, the optimal thing is to do this. That if Alice does that, then Bob will get the optimal strategy and Bob's chance will be higher to win the game. So when Bob receives y is equal to 1, we have shown that basically this task is to discriminate between these two ensembles. And if Bob receives y equal to 2, then Bob's task is to discriminate between these two ensembles. And you can see basically Alice's preparations are fixed. Fixed means only these 4 preparations Alice can prepare: P00, P01, P10, and P11. So for y equal to 1, Alice is making this ensemble by taking 0, 0, 0, 1 together and 1, 0, 1, 1 together. And let's say Bob discriminating perfectly with some measurement, these two ensembles. That means these 4 states are now fixed and Bob will get success probability 1. Right? Then in the second case, since now you can see that previously it was P00, P01. Now the sub-ensemble are defined as P00 and P10. And it can be easily proved that if Bob gets success probability 1 to discriminate for y equal to 1, the y equal to 2 will be maximally random. Only random guess will work for Bob and it will be half. So that means what is the total success probability? 1 plus half, 3 by 2 into half, because Bob has 2 input with equal probability. That is 3 by 4. That is the 1 CB Bob.
And vice versa.
And vice versa, of course. So for Bob if Bob receives y equal to 1, his task is to discriminate between these two preparations, P01 and P11. And for y equal to 2, it is P02 and P12, these two sub-ensembles. And what we have proved that then the average success probability will be mapped in terms of delta 1 and delta 2. So delta 1 is the preparation distinguishability between these two sub-ensembles, and delta 2 is the preparation distinguishability of these two sub-ensembles. Then one can get the 1 CB bound of average success probability, which will be delta 1 plus delta 2 less than equal to 1, because the classical bound is less than equal to 3 by. Yes, in qubit assisted RSC, that means in the quantum theory, what will happen? Alice's preparations are now given by the density matrices, and following the same definition, Alice will prepare this sub-ensemble by taking rho 00 and rho 01 together, and rho 11 by taking rho 10 and rho 11 together for x1 equal to 1. Similarly for x2 bit. And then one interesting thing happens that our preparation distinguishability definition was in terms of probability. So now if we need to make the map into quantum domain, that will be trace of measurement into state. Those are value states. So now for y equal to 1, Bob is trying to discriminate between rho 01 and rho 11. So I put it like that, rho 0y minus rho 1. And this half is coming from here. And then one need to optimize over all measurements. So that means it will give me an optimal measurement which discriminate these two states. And that definition actually fits into this trace distance concept, because this optimal measurement becomes the L-stop measurement for discriminating two states. In Qubit, we saw that delta 1 plus delta 2 should be less than equal to 1. For quantum mechanics, we have derived that the bound would be, the quantum boundary is delta 1 square plus delta 2 square less than equal to 1. So for optimal success probability, we just need to optimize these two, delta 1 plus delta 2, this quantity subject to this quantum constant. And then we will get back the well-known result of the optimal success probability. The important thing is, one can say here that for classical, you just put less than equal to 3 by 4 and you got delta 1 plus delta 2 less than equal to 1. So for quantum, why you didn't do that? For quantum, if I do that, I will get this thing. That delta 1 plus delta 2 less than equal to root 2. But as you can see, this is not the quantum boundary, because RSC is not the exhaustive game in a prepare measure type of quantum correlation. So that means our preparation if we characterize preparation distinguishability as a prepare measure resource in 2-to-1 type of RAC scenarios, it actually characterizes the quantum boundary, but the RAC witness cannot. For RAC optimum, this is only the point, but this is the quantum boundary, which is different than what RAC's optimal probability is giving. Now, by identifying this resource, we are now in a position to understand the connection with the measurement incompatibility of Bob. Then we will get a trade-off between these two resources. So, as I have said, for the sequential kind of scenario, Bob need to perform answer measurement. So we take these two answer, Bob's two measurements are answered with answerness parameter lambda y, which lies between 0 and 1. It is just a noise parameter. That means this is a noisy projective measurement with white noise. This is the effect operator of, I have written it as a curly B because it does not have any meaning in quantum mechanics. So it is the POV. Now, inside measurement and qubit preparation, the average success probability will then be mapped as lambda 1 delta 1 plus lambda 2 delta. And quantum advantage is obtained whenever this will be greater than 1. Because for quantum advantage, we need this to be greater than 3/4. So this to be greater than 1 subject to this constant, because this is the quantum correlation domain. This is the quantum boundary. And what we have found, a very nice result, that this quantum advantage implies
delta 1 and delta 2.
Huh?
Delta 1 and delta 2, what is it?
And delta 1 is the preparation distinguishability between these two sub-ensemble, and delta 2 is same for y equal to. When Bob y equal to 1 is selected, Bob has to discriminate between two sub-ensemble, Alice will send to. Now we got this nice connection that whenever Bob there is a quantum advantage, this becomes a necessary sufficient condition for Bob's measurement incompatibility. So in a way, by identifying this preparation distinguishability as a resource, it is one of the operational criteria to check whether two given measurements are incompatible or not. Because how many operational criteria we know for checking joint measurability? CSSH is one of them. One need to check whether it is violating CSSH or not. But CSSH experiment is difficult than the prepare measures. Let's say Bob's two measurements are answered with equal unsharpness parameter. Then we get the critical unsharpness parameter to ensure the incompatibility. Hynoseries result says that the critical parameter should be 1/√2. Now let's see as a function of preparation distinguishability. So this is this orange curve. So intuitive, this is very intuitive because as one can see, if the preparation distinguishability goes close to 0, that means the quantumness in Alice's side, if I try to decrease it, I need to increase the quantumness in Bob's side. So the Bob's measurement need to be more incompatible. Lambda should go towards 1. Because this is very intuitive to maintain the RAC advantage. However, if we take this scenario when Bob's one measurement is projective and another measurement is answer, then some counterintuitive things happen. That the Alice's side preparation distinguishability, if it goes towards 1, that means again towards the classical boundary. So the intuition is Bob's incompatibility need to increase more, but it happens almost joint measurable measurement will also give you the quantum advantage. So that means this is the regime where the encoded information can be preserved optimally. And that's why many receiver can get quantum advantage. Yes, so in preparation distinguishability approaches towards classical bound, nearly compatible measurement can give a quantum advantage, and this becomes the recipe of getting the arbitrary number of receiver which the earlier has missed. So now this becomes just the technical. I will just take the result that we have actually proved extensively. I'm not going into that technicality. That one of the Bob's measurement, each of Bob's first measurement is projective, second measurement is answer. The only thing we have, and after Bob 1's measurement, let's say Alice prepares this state, rho x1, x2. And after Bob 1's measurement, the state available to Bob 2 is the state after this channel action, Bob 1's channel action. So in general, I have written it like that: the state received by Bob K when Bob K minus 1 performed one answer, one serve. So phi is the effective non-selective channel. The nice thing, and then for Bob K, we have to define the delta K again. We have to define these marginal states similar to the initial case, and then we have to define the delta. The first non-trivial thing I need to comment that, let's say Alice prepared a 4 state, and then one of the state Alice gave to Bob 1. And Bob 1 will perform the Hellstrom measurement to optimally discriminate. Now, after Bob 1's measurement, when the state available to Bob 2, who says that same direction measurement we can take, because after the measurement, maybe the state rotated in the block sphere. So the Hellstrom measurement need to be changed. But what we have got that after this type of channel action, it does not rotate the block vector of the state, it just gets reduced. So that means for each Bob, the Hellstrom measurement is fixed. And by identifying this nice feature, the calculation becomes simpler. And then we saw that how the preparation distinguishability get diminished in after each Bob's measurement, that the first preparation distinguishability becomes function of answer parameter, and the second one is a scaling factor. And in that way, the few remarks are: if any of the Bob measure two short measurement, then as I have told that it will not give any more Bob quantum advantage. So essentially, we proved this theorem that if we parameterize this two preparation distinguishability like that, then we have shown that each Bob can have answer parameter between 0 to 1. So that means they are valid answer parameter such that all Bobs will get sequential quantum advantage. So I'm not going into this detail of the proof. The trick is to show that lambda become a monotonically increasing function, so that the average success probability will become decreasing function, but will always have greater than 3/4. So in sum, we have shown arbitrarily long sequence of receiver can obtain quantum advantage in sequential 2-to-1 RSC, and we have also identified a new operational feature of a qubit in terms of preparation distinguishability and the trade-off with measurement incompatibility, and how they form a necessary sufficient condition for joint measurement. And also, this is the first time we have shown that for arbitrary sequence, one-to-many communication protocol, not only across space, but also across time. There can be many future scopes, like how we can apply this preparation distinguishability in other prepare measure-based communication tasks, and then we can try to build up a general resource theory in the prepare measure scenario, which is still not there in terms of preparation distinguishability and measurement incompatibility. And maybe other families of preparation and decoding measurement can also give you the arbitrary sequence of observer in different prepare measure tasks as well. And also whether this preparation distinguishability can put a restriction in vectorology and sense, the limit of quantum sensing. And in our group, we work on these topics like entangled quantum correlation space and quantum correlation in time, communication, randomness certification, and also variational quantum algorithm, error correction, dynamical decoupling, parameter estimation of environmental noise. Because to do these kind of things, you need noisy parameter estimation, and then you need to mitigate it via dynamical decoupling and error correction. And also, I must say that we have several positions for PhD and postdoc, and also some summer visit or winter visit kind of thing is available. So if someone is interested, please send us email, and we will then try to collaborate. So yeah, so thank you. This is, I must say that uncertainty is fundamental. So keep calm and be random. Don't be sure about anything. So thank you.